Hi, we're Group AB5, and this is our design review presentation.
The first step in the iterative process of reviewing our repeatable vehicle design was to carry out structural changes to the main and the IMECHE wooden board. We decided to modify the protruding sides of the lower wooden board as it needs to minimize mass and thus maximize velocity. This was carried out by cutting the two external sides, and it allowed us to save 84 grams of mass, resulting in an 11.4% mass decrease from the original frame. We also had to extend the front of the wooden board by around 8 millimeters and move the tactile switch by 15 millimeters from its original position, in order for the rack to extend to the complete displacement of 175 millimeters necessary in the longest 4-meter run. Furthermore, we included other minor changes in the cab model to ensure greater stability as suggested by the panel. This included the addition of 4 hex drives under the head screws for each of the 4 plastic axle brackets for a total of 15 screws, which would pass through manually drilled holes in the wood. We also inserted the 4 Phillips rounded head screws which come with our selected motor, and also inserted a singular screw for the unnecessary plastic double gear which was not originally attached to the motor. To make the model as accurate as possible, we also included the steel brass plated toe at the end of the model so it would appear in the company.
So as you can see, here is our Excel spreadsheet with all the relevant data for the materials involved. Essentially in column B, we decided to split up the materials into sections. Looking at certain components, we see that we have an issue number 01 and a revision of A, which tells us that this is the latest version of the product available. Looking at the type column, the components we have picked is for 4 different types. An example being our DP/DT switch, which we have classed as a standard item. The reason being is easily found and is mass produced by many suppliers. Next, the part number is automated from the Excel spreadsheet and essentially combines the first 4 columns to produce the part number. Similarly, for the full cab description, it's also automated and is produced from the first 5 columns. For the density and mass column, we sourced the density information from supplier's website. However, the mass was calculated by us by using the dimensions provided to work out the volume, then using this with the density to work out the mass. The total cost of all of our components ended up being 29.98, which perfectly fits in our budget of £30.
As for the engineering science behind the wiring, as you can see on the left of the diagrams is the internal wiring for the DP/DT switch between its terminals. On the right, the wiring of the entire circuit is shown for the forward rotation. We can see that when the switch is pushed in the forward direction, the point A is connected to point C and point B is connected to point D.
Model representative of the simulation, we had to take into account external forces such as drag force or rolling resistance, which negatively affect the overall net force and acceleration of the car respectively. To calculate the rolling friction force, we used the following formula. We took the coefficient of friction as 0.085 to make our model as close to the simulation as possible. As you can see from the spreadsheet, it was kept constant at 0.837 newtons for values where the velocity was not 0. For the drag force, we used the following formulas and assumed the coefficient of drag to be 1 after conducting some research with similar shapes, and as you can see, it increased proportionately to velocity squared to a maximum value of 0.00129 newtons. To increase the top velocity, we use the same velocity model used in scenarios 1, considering drag and rolling resistance, which negatively affects acceleration and hence top speed. We decreased the gear ratio from 256 to 64, which increased the velocity by more than 120%, achieving a top velocity of 0.485 meters per second, as we can see from the graph on the right.
To better understand how different parameters affect the total energy usage, we created an energy model to mimic the simulation energy output. We did this using the formula drag force times distance moved per time step, calculating the energy used to compress the spring and accelerate the car, and add all the energies together to obtain the estimated total energy usage. In order to keep the energy usage as low as possible, maintaining a high velocity, we tested different values for radius, chose the most optimal one. In our simulation, we obtained total energy of 2.75 joules to complete the route as shown in the graph on the right.
From the IMECHE simulation app, we have completed a virtual animation of how the challenge would be completed. During the previous Q&A, there are 2 main areas of focus, the wiring and the distribution of mass in the car. As of right now, the level of expertise required to properly model wiring in Fusion 360 is too high for our team, which is why we'll work to improve on such aspect of designing in Fusion.